So good day everyone, this is Mabel and Lola, and for today's discussion we're going to solve one of the problems of combined axial and bending stresses. Our reference book here is from the Lasagna. So we have here the problem: steel column 3.6 meter long and hinge at both ends is used to carry an axial load of 1000 kilonewton. The column is subject to end moments reverse curvature with m sub 1 equals to 90% of m sub 2. Fy is 248 megapascal. Modulus of elasticity is 200 gigapascal, and the allowable stress is 115 MPa, and the allowable bending stress is 149 MPa. For the properties of the section, we have A equals to 0.013 square meter, S sub x equals 0.00012 cubic meter, and R sub b equals to 94 mm. Our task is first to determine the computed actual axial stress of the column, then to determine the computed actual bending stress of the column, and last is to determine the moment capacity of the column. In computing the axial stress, we have here the formula F sub A equals to P divided by A, where P here is the axial load of the column and A is the cross-sectional area. So filling up the given values in the problem, we have 1000 kilonewton for the P and 0.013 square meter for the cross-section area. Dividing those two values, we obtain the value for the computed axial stress as 76,923 kilopascal or 76.923 megapascal. So in letter B, we are to determine the computed actual bending stress. So before calculating the actual bending stress, we will determine first if the column here is in large or small axial compression. So to determine, we have here the ratio of F sub A, which is the computed actual axial stress, divided by F sub A, which is the allowable axial stress, and we obtain the value as 0.669, which is greater than 0.15. Therefore, our column has a large axial compression. So since it has a large axial compression, the column or this member must satisfy the following requirements, which is the stability interaction criterion and the strength interaction criterion. We cannot solve it right now because there are two missing values, which is the reduction coefficient and the Euler's stress. As mentioned earlier in the problem, we have here a reverse curvature, which is said that if our column is in reverse curvature, therefore the coefficient of reduction is equals to 0.4. So to check if we will be using the 0.4 value, we will be using the equation as 0.6 minus 0.4 times m sub 1 divided by m sub 2 for rotationally restrained compression member. Take note that in the given problem, we have the value for m sub 1 as 90% of m sub 2. That's why our m sub 1 here is 0.9 m sub 2. So canceling similar terms, we obtain the reduction coefficient value as 0.24, and it is lesser than 0.4. So therefore, we will be using the 0.4 as the value for the reduction coefficient. And for the Euler's stress, we have here the formula F prime E equals to 12 times pi squared times the modulus of elasticity divided by 23 times the K times the length of the column divided by radius of gyration squared. So substituting all the values, and our K here is 1 since it is the recommended design value. So we obtain the Euler stress value as 702.16. Now that we have obtained the two missing values, we can now solve for the stability interaction criterion and the strength interaction criterion of the column. So we have here first the stability interaction criterion with an equation of computed axial stress divided by the allowable axial stress plus the reduction coefficient times the actual bending stress divided by the quantity of 1 minus the computed actual stress divided by the Euler stress multiplied by the allowable bending stress equals to 1. So as you have noticed that in our original equation for the stability interaction criterion, there is the reduction coefficient y and the bending stress y there. We didn't include that in our equation here since the direction of the bending is in x direction. That's why we disregarded the equation of the y components. So continuing, we have here the values as 76.923 divided by 115 plus 0.4 times f sub b divided by the quantity of 1 minus 76.923 divided by 702.16 times 149, and we obtained the value of the stability interaction criterion as 109.82 megapascal. This will be the value of our bending stress for the stability interaction criterion. Same with the strength interaction criterion, we still disregarded the bending stress in y component. So we have the equation here, the computed actual stress divided by 0.6 Fy plus the computed actual bending stress divided by the allowable bending stress equals to 1. Substituting the values, therefore we obtain the bending stress or the computed actual bending stress of the strength interaction criterion. In letter C, we are to determine the moment capacity of column using the equation of F sub B, or the Computed actual bending stress equals to M, which is the moment capacity of the column, divided by S sub X. So we have here F sub B equals to M divided by 0.00012, which is given already in the problem, times 1000 to the power of 3 equals to 71.97. So rearranging the equation, we obtain the value of M as 8,636,400 Newton millimeter, or 8.6364 kilonewton meter.